Compared to my last video that was clearly utter chaos in California, here I am in Vermont in utter peace and quiet. I'm in Arnold's Bay, which is where Benedict Arnold did something heroic. And I'm here with the dogs, and they're pretty quiet. And this will be a math video about a counting system I invented that generates polynomials, kind of like Euler's prime generating polynomial, that generates primes. So, away we go. To create a one-way hash function that was different than the one in my last video that I used as an example to show how a one-way hash function works. And I accidentally created a counting system. And it's really interesting how the counting system works. I use only one symbol and a 0. Even though it's not binary, it's a base 5. But it mixes the two, because when I come up with a number using ones and zeros only to express base 5 value, I got what could be read either way. This series of ones and zeros can be interpreted as two different numbers. And what that actually does is that, like grade code, that's what I want to mention, because when I checked to see if something like this had been invented before, I found grade code, which is similar to what I developed. But I believe grade code is still on a binary counting system, where mine's on base 5 versus base 2. Now, my counting system generates polynomials, and in turn, the polynomials sift out primes, semi-primes, and spheric numbers. A spheric number is a composite number made up of only 3 primes, no more than 3 prime factors. So, and what else is interesting is the counting system also accounts for 2, even though it's an even number. Although it doesn't sift out even numbers that are divisible by 5. But it does still skip over quite a few numbers because of the way the counting system gives you a sequence of polynomials that leaves out a whole bunch of even numbers and even some of the primes. Now here's how the counting system works. Let's start with 1. Amazing. Let's not go there again, guys. Shh, quiet. Hi. Leave the fisherman alone. You're going to scare away the fish. You want to see some action, huh? Yeah. Shh, shh. Lay down. Okay, so that's not surprising that that's 1. That's 2. That's 3. We almost have a base 1 system going on here, and that explains the bases to somebody that may not be familiar with bases and changing base systems. If we had a base 1 system, I'd have to do that 1,000,000 times to express the value 1,000,000. So we use a combination in binary of just ones and zeros, because a computer switch can only be on or off. But that series of ons and offs, so ones translate to ones and zeros. Those ones and zeros, because of the way they're positioned, if, for instance, in a base 10 system, I put a 0 at the end of that, okay, just with those 2 symbols, and 4 symbols, I should say, I'm expressing a number 1,110, okay? But let's continue on. This, not surprisingly, is a number 4. Okay, so now we have a base 10 system that said because we have 10 fingers. And that's even why these things are called digits, all right? But as a religious guy, a lover of God, I like to think that the universe was created by the hand of God. They talk about God using one hand, possibly because he's omnipotent, so he can do an entire creation of the universe job with just one hand. So, being base 5, that's why we need 4 symbols and the 0 as a placekeeper. Now, as soon as I go like this, okay, that's a set of 5. And a set of a complete base will always be the first symbol of your base with a 0 after it. So in a base 10 system, we would have one set of 10. And then when we go to 11, we have a set of 10 with one left over. The what I call bin 5 system, you would go instead, just like with the decimal system, you put a 1, and then the 0 after it is like you're lying through it, because with a decimal or base 10 system, we have 9 symbols, 1 through 9 plus the 0. So we don't have, that's a place system. So now, this 10 represents actually a quantity of 5. Okay? So now, if we want to continue to 6, look at this interesting way I use the 0. We've got a set of 5 and one left over. Okay? So now, that number in decimal, okay, could be translated into decimal as 101. In binary, what would that number be? Okay, so we want to count in binary. Well, I believe that number is 5. Watch. In binary, you have 1 plus 1 equals a full set of 2 with none left over. Then you add 1 and you get a full set of 2 with 1 left over, which equals 3 in decimal. Okay, that equals 2 in decimal, and that equals 1 in decimal. Add 1, and we get 0, because it's a full set. Okay, carry the 1, we get another 0, because it's a full set. And carry the 1, and then bring the 1 down, because there's nothing under it. So that equals 4. Looks like 100, but it equals 4. Now, decimal, it would be 100, obviously. So now we add a 1, and we get 101. And that is the number 5, expressed in binary. However, it's the number 6, expressed in bin 5. So this can be translated as 3 different numbers, or limitless numbers, really, if depending what base system you're using. Now here's the notebook where I'm trying to get past 1200 and take all of those numbers and translate them into bin 5 and add, and then once translated into bin 5, translate them into the binary number, which I haven't done that yet. Here it is translated into bin 5. I think you can see what's going on there. I'll hold this straighter. There's other experiments in there. I've got notes and things. I don't even remember what I was thinking when I wrote them, but figuring them out again makes them stick. So as you can see, here, I've also got the binary value. So take 490, okay? 490 into bin 5 is that. Because we've got 3 times 5 cubed plus 4 times 5 squared plus 3 5s being 15. So 15 plus each of these is 5 squared, meaning 25. So that's 100, giving us 115. Then 115 plus 375, because we got 125, 125, 125, which is 5 cubed, 5 cubed, 5 cubed, gives us 490, okay? But wow, when we take that and punch it into a binary to decimal converter, we get this value in binary, 7,662. Now, every fifth, that's obviously not a prime because it's even, right? But that's the thing with my counting system, is that every fifth number ends in a 0. And if you convert any binary number that ends in a 0 to decimal, you got an even number. So it goes, even odd, as that last number changes back and forth from a 0 to a 1. But then, it's important, if you want to grab some more primes, for some reason, because this is the other thing that kind of baffles me. I'm getting this system of polynomials that I'm trying to understand. You add 4n plus 3 to these values, and you pick up more numbers that can be tested as primes, and I'm sure you'll find out they keep coming out prime, semi-prime, and spheric in about the same ratios. But I know I have to go a lot higher than 1200 to see what goes on here. Now here's an example of some polynomials around 466 and 467. And by the way, this Einstein is not the Einstein everybody knows and loves. This is a different mathematician, Einstein, that came up with his own primes that are congruent to 2 mod 3. And you'll see that here, I think, is what we got going on with a lot of these. These polynomials, when we convert them over and put them through the 4n plus 3 function, it's really interesting what's going on. Lots of different things. But let's start at the beginning. I like the way the counting system even accounts for 1 and 2 becomes the prime 3. Okay? Yet, as you get down to here, where you add the 0 on, which usually bounces us out of the primes and gives us an even number, this even number is a prime. And now that continues on, and we keep translating these numbers into from bin 5 to binary as we go down. And that's the sequence. And I'm going to keep this sequence going all the way to 1200, and then by hand, and then when I get a computer, the fun will really begin. We'll really start analyzing this, because once I looked at this sequence, I noticed that this is what it's doing. It's going 2n plus 2 every 5, and 2n plus 1 every time. See? 2 times 2 is 4 plus 1 is 5. 5 times 2 is 10 plus 1 is 11. 11 times 2 plus 1 is 23. 23 times 2 is 46, plus 1 is 47. But then becomes the fifth, we start a new set of 5. So when we start a new set, then our bin5 number ends in a 0. See? On this number we have a 5. So we have 2 times 5 being 10 with none left over. See, that's the number we're trying to replicate and express, I should say. And then we change it to binary and we get the number 6, an even number. And that continues through. But although even, it's spheric. I'm sorry, it's semi-prime. This is our chart. Prime is pink, semi-prime is orange, and spheric is yellow. Now, I noticed that if we take these numbers and add them, we end up, or I should say, put them through the 4n plus 3. In other words, put 0 as the n. We get 0 plus 3, which is 3. We put 1 through, we get 7, and so on. Then quite a few of these numbers show up here. And I think that's because we're adding those two polynomials. But this I still have to analyze. Here's an interesting number. The 520 I call the Happy Days palindrome. Why? Because when I turn that into a bin5 number, I got, if you count the leading 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0. So it's a palindrome. When you convert it to decimal, this starts a new set of 5. That's therefore the 0 and the divisibility by 5. And that is number 1950. So I'm thinking like 1950s was the Happy Days, like the Fonz and Richie Cunningham and all that. And here's the whole page. And these are the 4n plus 3s. And it's interesting that if you change that to negative, or basically subtract 3, how you get a lot of interesting even numbers that all coincide. I like this 436, 437, 438, because when we take those, translate them from bin5, we get 3 primes in a row, 1901, 3803, and 7607. And each of those, if you put them through the function 2n plus 1, as the n, that's exactly what happens. They become that sequence.